Sorry. Are there any questions before we start? All good. Okay, so let me just give you a review of what we did last time yesterday. Okay, today's lecture 16, I believe. So what was happening yesterday? So it's essentially the idea is like when you have like a graph of a function of one variable, right? If you wanted to find the tangent line to that function, right? The question of the tangent line needs the first derivative, right? Because the first derivative is kind of the slope. So the equation of tangent line needs f prime of x, right? What I was trying to say is that, there's nothing that says that you can only approximate a function or like find the tangent line to a function. There are other things besides lines that you could try to use to approximate a function. So another thing you can do is to try to approximate a function by a quadratic polynomial. Okay, so you can try to approximate like a function by like a polynomial of degree 2, so you could call that approximating polynomial, although no one uses that word, that phrase. So like approximating quadratic polynomial. Right, which the equation was, if this is A, the equation was f of A plus f prime of A times x minus A plus 1/2 f double prime of A x minus A squared. So the whole point, the reason why I'm bringing this up again is that when you look at this equation for the polynomial of degree 2 that you use to approximate the curve, it involved the second derivative in addition to the first derivative. So the second derivative, in a sense, is used, the point of the second derivative is to help you find this polynomial. And if you look at it, the second derivative is whatever is multiplying the stuff that has x squared. So if you remember like the review of polynomials that we did yesterday, when this coefficient is positive, right? And so this is what you need to remember from yesterday. If the second derivative is positive, the trick, to memorize this is that you make a face whose eyes have the sign of the second derivative. So here the second derivative is positive. So you make a sign where the second derivative, you make a face where the eyes are positive. And if you're positive, that means that you're happy. Okay, so in this case, the polynomial is concave up. But if the second derivative was negative, right? If this coefficient is negative, then again, you can make a face and the eyes of the face are the sign of the second derivative. And so the polynomial now, the face is sad. And so the polynomial is sad or concave down. Is that making sense? So here it looks kind of like if you look at this area, right? It kind of looks like the function is kind of sad, meaning that like when you approximate it by a polynomial of degree 2, it looks like it should be approximated by a concave down polynomial. Is that making sense? And here it also looks like sad. and then it was happy here. So you can kind of start playing around like with the graph and just check in which regions like the polynomial would be concave up or concave down. Is that making sense? Any questions about this? So that kind of is I mean, so like the interpretation of like so just to so the interpretation of the first derivative is that it has to do with the slope of the tangent line, right? It is the slope of the tangent line. And the interpretation of the second derivative, because of that, the second derivative is basically telling you the concavity of the function, what we call the concavity of the function, meaning that whether like the way it's bending, like in a sad way, like in here, or like a happy way. So it has like the second derivative has to do with how the curve bends. It has to do with the concavity. Is that making sense? Are there any questions about this? So again, first derivative is slope. Second derivative is more like the bending of the curve. So just based on that, what would you say? What would you say? What should be? What should be the second derivative of a line? So just this is more like a conceptual question. What would you say is like the second derivative of a line? So here's a line, right? Think of it as a curve. What would you say its second derivative equal to? Um, does a line bend? Yes or no? A line doesn't bend, right? So if you think about the equation of a line, is mx plus b, right? The first derivative is m, right? But m is a constant for a line, right? So the second derivative is 0. So the second derivative is just 0 because the derivative of a constant is 0. So that's saying that if the second derivative is always 0, that means that the graph of the function never curves itself. So it must be a line. Is that okay? Any questions about this? So the idea is like once you have the help of the first derivative and the second derivative, you can actually start sketching the graphs of functions pretty decently. So let's try to do some sketches of graphs to have like an idea of how this works out. So let's try to find like the graph. So here, so let me make this remark. Using the first and second derivative of a function, one can make a pretty good guess about the shape of the graph. So let me give you an example, a couple of examples about this. Okay, let's do one that we have kind of analyzed before, but this is a nice one to have. So a typical problem like this would be to sketch the graph of something like y equals x cubed minus 3x. So let me do that here. So for these sketch problems, what you have to do first is always find the first derivative and find the second derivative. So here's like the steps. Let me write them. And these steps like you should do all the time. So you find the first derivative, find f prime of x, find f double prime of x, determine the critical points of f, also determine where f of x is increasing or decreasing. And this uses the concavity, this uses the first derivative. and then determine where f of x is concave up and down. This is the second derivative. Just give me 1 minute. Okay, did everyone? Okay, so hopefully everyone had a chance to copy it. So let's try to apply these steps to this problem. So step 1 is to find the first derivative, right? The first derivative is just going to be 3x squared minus 3. Step 2 is to find the second derivative. And the second derivative is going to be what? Just 6x, right? And step 3 is to find the critical points. Remember, the critical points are where f, the first derivative is 0. So, I mean, we have actually done this example multiple times. Anyone remembers what the critical points were in this situation? Yeah, they were 1 and -1. Good. Okay, now comes the old step 4, even step 4 we had done before. Okay. So step 4 is where the function determining where the function is increasing, decreasing. That requires the first derivative. So you remember what we had to do in step 4 was to analyze the first derivative. So if you can write it in a way that's slightly more useful. So what you do here is like to analyze the first derivative, you make a line. On the line, you identify the critical points. Okay. And then okay, and then you just what you would do is like to just test some values. So for example, if you chose like the value for 0 here, if you chose 0 here, the first derivative gives you a negative number. So it was negative here. So that means that the function was decreasing. And if you chose like 2, for example, the first derivative was going to be positive. And if you choose like -2, for example, the first derivative was also going to be positive. So again, we did this before, but for the first derivative, that's kind of how the function looks like, right? Is that making sense? So here is increasing, decreasing, increasing. Is that okay? Okay, and then for the last step, you have to determine where the function is concave up and down. Again, the concavity is in terms of the parabola, so that just means you have to determine, and the parabola has to be in terms of the second derivative. So really the concavity, finding where the function is concave up or down just means find where the second derivative is positive or negative. So what determines in this case, for what values of x is the second derivative positive, and for what values of y is of x is the second derivative negative? So what's the thing that decides here positivity or negativity? Well, it's going to be you know, 0. If you choose a number that's bigger than 0, right, the second derivative is going to be positive. Again, what the second derivative being positive, you can actually do write 2 pluses here, because that would tell you that it's concave up. And if you choose a negative value for x, the second derivative is going to be negative. So it's going to be concave down. Is that making sense? Any questions about this up to this point? Because now what I will do is just do the sketch. So it's kind of important to make sure that algebraically you know how to find all these steps before like proceeding to the sketch. And by the way, here we have well, okay, so here's how you would think about the sketch. So again, the function was x cubed minus 3x. So what you can do first is locate, you can locate first the critical points. The critical points were 1 and -1. So let's put here 1, and let's put here -1. Okay, and what are the values for the function there? At 1, right? At 1, the function has values 1 minus 3, so that's -2. And at -1, the function has values -1 plus 3, so that's 2. Right, so I'm just saying that f of 1 is -2 and f of -1 is 2. Is that making sense? Everyone is okay with that? And okay, cool. So again, you look at 1. If you look at 1, right, 1 is bigger than 0. So 1 falls in the regime or in the location where like the function is concave up. So what that means is that near this critical point, the function looks like a happy face. So you can draw like a happy face near this function. Let me use a different color to like indicate how you start drawing it here. Okay. And near -1, the function is concave down, right? Because -1 belongs to this region. So you can draw a sad face. Is that making sense? Yeah, no, this it's usually there's always usually like a problem where you're asked to graph it. Yeah. It's kind of like one of the key things of calculus, like high notes, like to grab a function. So and then you kind of just like then you kind of like check these things that okay, you know that after 1 the function was increasing, so this just means that you should just continue doing this curve like increasing. Okay, before -1 the function is also increasing, so the function is doing something like this. And then between -1 and 1 the function is decreasing, so you kind of like join them like this. And that's more or less how the graph should look like. Is that okay? Is that making sense? So let me show you on the algebra that in fact this is correct. So f of x is x cubed minus 3x. And so you see it kind of looks more or less like what I did. Here you have 1 comma f of 1 and -1 comma f of -1 is there, right? So that's like we got like a pretty good sketch of the function just by you know, using the first and second derivatives. Is that okay? Are there any questions about this? So notice, I don't know if you observed this, but let me just waiting for the iPad to show again. So if you notice, before 0, let's put 0 here because it's kind of an important value as well. Before 0, the function was concave down, so it looks like a sad face, right? And after 0, the function looks is concave up, so it looks like a happy face, right? So if you thought in terms of moods, the function changes from sad to happy, right, at 0. So you say that the concavity is the concavity change at 0. So you call that an inflection point. Okay, so an inflection point is just one where the concavity changes. Let me define that for you. So here, let me put this like concavity changes. So it's inflection point. It only occurs, it's kind of similar, it's kind of like the version of critical points for the first derivative. So these only occur where the second derivative is 0 or is undefined. Can occur. It happens only at the points where the second derivative is 0, or can only happen is that making sense? Any questions about this? So let me give you an example for you to work on, and then we'll discuss it together. Do it together, but it's good for you to try it on your own first. Let's see, another polynomial. Yeah, okay, try to do this for this example. Try to sketch okay, so I'll give you I don't know, let's talk. This one can take a little bit more time, but let's combine it with the bathroom break that we usually give. So let's take at least 6-7 minutes for you to work on it, and then I'll do it for everyone together. So yeah, I'll pause briefly so for you to get a chance to do this. But this means find the first derivative, find the second derivative, find the critical points, find where the function is increasing and decreasing, concave up and concave down. So just follow the same steps that you saw me write a couple of minutes ago. Okay, so yeah, let's meet like in 7 minutes and discuss it. Okay, let's try to do this to see if everyone found the similar sketch. So what colors was I using? Purple and green. Let me check. This is okay. So first derivative is what? 4x cubed minus 4x, right? It's kind of one of these things. Like for finding the first and second derivative, you actually don't want to simplify them too much. So, but then for finding the critical points, you do. So here you could try to factorize like a 4 or an x, but it's better not to do that until you have computed the second derivative. So the second derivative would be 12x squared minus 4, right? Everyone so far so good. We're all good with that. Now you have to be careful. Okay, this is actually a good example because here's where the algebra is not too complicated, but it can give you like can present like it's easy to just like forget certain solutions. So the critical points again is where the first derivative is 0. So if you factorize, the philosophy is you should try to factorize as much as possible. So the thing that you can factorize here is like a 4x. So when you factorize a 4x, you get x squared minus 1, right? Is that making sense? So the critical points are actually 3, which are x equals 0, x equals 1, or x equals -1. Is that making sense? So the only thing that I'm saying it can be confusing is that sometimes when people see this, right, they will divide by x. And if you divide by x, the problem is that you miss out on x equals 0. So do not divide by x. I mean, so try to factorize as much as possible to not lose solutions. So do not divide by x, divide here by x when simplifying. By x when simplifying. Is that making sense? And again, that is like the only part that can get tricky because the algebra itself, like usually you'll be given like a problem. I'll give you like a problem where it's easy to factorize things and things like that. So it's not, it's more like forgetting certain solutions because like you divide it or things like that. That can be tricky. Okay, and then what comes next is to analyze where the function is increasing, decreasing, and all that stuff. So where is the function increasing? Again, the first derivative was 4x times x minus 1, x plus 1. So what you should do here is, again, draw the number line. You put 0, 1, -1. And again, you have to test some values. So for example, if I choose a value 2, if I choose a value 2, the second derivative will come out as positive. Sorry, the first derivative. I'm not sure why I said the second derivative. So that means that the function is going to be increasing. If you choose something like here, like -2, this would be negative, negative, and then negative. So 3 negatives. Wait, yes. Yeah, so they should be negative. Oops. Yeah, is looking good. And then you just have to figure out the other two. So you can put like 1/2, you can choose 1/2 here. If you choose 1/2 here, this is positive, this is negative, and this is positive. So there are two positives and one negative, so that gives you a negative sign. And if you choose something like -1/2 here, you get a negative, negative, and positive. So you get positive. So you're getting decreasing, increasing, decreasing, increasing. Is that making sense? Questions about this? And so in the last step, we have the second derivative, which was 12x squared minus 4. Again, you want to factorize as much as possible. So we can factorize first an x squared, so you get 3x squared minus 1. Is there anyone can see a way to factorize this a little bit more? What can you do here? How could you factorize this further? Any thoughts? Well, you could use the difference of square formulas. Is that making sense? Yeah, it's almost, you have to be careful. You cannot take the 3 that way. You have to leave it at, it ends up being square root of 3. So what you can do now is in this number line for the second derivative, the interesting locations now are 1/√3 and -1/√3, because that's where the second derivative becomes um, becomes 0. So you see, to analyze the sign of the second derivative, for example, if you take a number bigger than this one, what's a number bigger than this one? I mean, you can take something easy like 1. If you take 1, if you choose 1 here, this is positive and this is positive. So the second derivative should be positive here. Positive means concave up, so it means you're happy. And then if you choose a number in between, the easiest number in between these two is 0. So if you choose 0, you get negative, and then you get positive. So this is negative. So you're sad. Okay. And then the last one, you can choose something like -1. So if you choose -1 here, this gives you negative, and this also gives you negative. So negative times negative gives you positive. So it goes from concave up to concave down to concave up, or happy, sad, happy. Is that okay? Are there any questions about this? That making sense? Again, the algebra is not that bad, but it can be a little bit tedious because you have to check where these things are positive and negative. So just make sure not to go slowly so that you don't do anything too crazy. Okay, and with that, we're ready for we're ready to analyze where it becomes increasing, decreasing. So let me do that. Okay, so again, the function was the sketch like? The function was x to the 4, right? Minus 2x squared. Where we found 3 critical points. Let me put those in purple. Oops. You should evaluate the function at each critical point. So what do you get at 1? At 1, you get 1 minus 2, so you get -1. At 0, you get 0. That's good. And -1, what do you get? You also get -1. Okay. And then it's also convenient to draw here the numbers where the second derivative became 0. You can draw them with different colors so that it's not confusing because these are not critical points. Oops. These are just like the points that determine the concavity where it changes. So what is 1/√3? That's a little bit less than 1. That's all that you need to know. Okay. And what's -1/√3? -1/√3? That's also between -1 and 0. Okay. And what is f at those values? That's so let me just compute them here. So what is f of 1/√3? So that's 1/9 minus 2/3, right? Is that what you found? So I mean, the exact number itself doesn't matter too much. It's just to know that it's like a negative value and it's between 0 and -1. So you can put it somewhere in here. And the other one is going to be the same value, actually. Is that making sense? So far, so good? And here comes the fun part. So I would start looking at each critical point. So I look at this critical point. I would look at -1. You notice that -1 belongs to this area. So in this area, the function is happy, right? So you draw like a mini happy face near -1. Then for this point, for 1, which belongs to this area, the function is also happy again. So let's draw a mini happy face here. In fact, this is going to look better if I put the numbers 1/√3 and -1/√3 above the x-axis. So let's do that. Okay, and what about 0? Where is 0? 0 is in this region, so it's sad. The function is sad. Right? So far, so good. So you kind of copy mini parabolas near each point, and then you kind of try to join them using the properties of the increasing, decreasing. So for example, between -1 and 0, the function is supposed to be increasing. So you should just kind of like join these two segments, like these two mini parabolas. I mean, they're not really mini parabolas, but they look very similar to parabolas. So that's why I'm calling them parabolas. And between 0 and 1, the function is decreasing. If you look here, so you join these two. And after 1, the function is increasing. So you can do this. And then before -1, the function was decreasing, so it should look like this. And that gives you the sketch. Is that making sense? Is that okay? So let's see. So it is so we had 3 critical points, right? How many relative mean do we have? How many relative mean are here? Remember, relative mean is a bottom. Like if you think of the graph as a roller coaster, it's like a valley or like the bottom of the graph. I see 2 relative means, so there should be 2. Now, how many relative max are there? It's just at 0, right? And where were there inflection? Are there inflection points in this graph? Remember, an inflection point is just where the mood of the function changes from positive to negative, or happy to sad or sad to happy. So are there inflection points here? Well, let's see. Are there three? Actually, okay, so there is one here, right? And there's another one here, but if you look at the sign for the second derivative, it only the change. I mean, there are three regions there are three moods, right? You're happy, sad, happy, but that only happens. The change only happened at two spots, right? So there are three happiness, there are three mood regions, but that means that there are only two changes, right? I mean, you can think about it throughout the day. Maybe you're sad when you wake up because you wanted to keep sleeping, and then some point during the day you get coffee and you feel happy, and then the coffee energy runs down, and then you're sad again. So you had three moods, right? Sad, happy, sad, but the change only happened your change between moods presumably only happened at some point twice. So there are only two inflection points. Is that making sense? Well, let's see. Yeah, I can show you how it looks on GeoGebra. I had graphed it before. So x squared minus 2 x squared. And here it goes. It's essentially the same as what we found, right? So here's 0, f of 0, 1, f of 1. Those are I'm plotting for you the critical points so that you can see them. And then the inflection points happen at what? 1 over square root of 3. F of 1 over square root of 3. There's an inflection point there. I can use a different color. And then minus 1 over square root of 3. F of minus 1 over square root of 3. And there's another inflection point there. So you kind of see, I mean, it's kind of hard to tell, from the graph, it's harder to identify the inflection points, but hopefully you kind of should notice that the bending of the curve, the concavity has to do with in what direction, the curve is bending. And so, here, if you think of it as a wire, here it's bending one way, and then it bends a different way, and then it bends another way, which is kind of this related to these mood swings, mood changes of the function. Right, so you can think of the curve as some like a wire that you can build up the curve from pieces, right? Mini wires. So it's kind of where connecting this piece to this piece to this piece to this piece to this piece, and then gluing them all together. But when we're gluing them, we are kind of changing the bending of the curve, and that has to do with the concavity. Is that making sense? Okay, so this is a good example, some good examples about how to sketch functions. I think for now I think it's a good number that we have done. So the next application, so if you notice, right now we are starting to see more useful things that you can do with calculus. So now we're learning how to sketch curves, which is a fun thing to do. The thing kind of that makes calculus powerful is that it can be used for optimization problems. So an optimization problem is just to identify where a max or a mean occurs. of a function that you care about because it has practical applications. So let's take a break because it's slightly different topic, like 5 minutes, 5-6 minutes, and then I'll start doing some examples of optimization problems. The good thing is that you don't have to learn anything new. It's just like applying what we have learned so far. Okay, so let's take a break and then we'll come back to that, if that sounds good. Okay, so this is a cool topic. It's actually one of the better topics of calculus. It's what makes calculus so powerful in a way. We'll start slow, and tomorrow we'll continue doing examples and applications because it's like yeah, it's kind of entertaining. Let me start here. Yeah. So here's like the most basic optimization problem probably of all time. You actually don't need calculus to solve it, but it's kind of nice to do it with calculus. So you're going to build a fence. Oh, sorry. You're building a rectangular garden, and you're going to build a fence around it. So you have a rectangular garden. So you want to make a rectangular garden. Okay. Okay, let's say when you are building it, you will maybe would like it to be as big as possible, but you only have so much money. You don't have infinite amounts of money, so you only want to spend money. The money that you can spend on it allows you just to build a fence, like let's see, 100 feet. So the fence in total will be 100 feet. Well, this may not be too much, but it's just to give it's just trying to find like a number that's good to work with. Okay, so here are like some possibilities for this garden. Let's try to think of some. Let's say this side is 5 feet of like this side is going to be 5 feet. This other side is going to be 5 feet, right? So the perimeter, like the fencing, right, is a total of 100. So how much for a rectangle? How much should each of these sides be? Good. It should be 45 feet. So what's the total area that if you decided to build the garden this way, right? What would be the total area of this garden? It would be 5 times 45. You can do it, and it's 225. So it's 225 feet square. Or square feet. So far, so good. Everyone okay with that up to this point? But maybe you decide to make it a little bit wider. Okay. So now how much should the other side be? Like the other two, how much of each of the other two sides should be? Uh, should be 38 actually. So in fact, this picture is, but you were close. Yeah, I mean, yeah, it should be if it's so I'm doing it wider, so but yeah, it should be 38, I think, because what you want is these two sides to add to 50, and so 50 and 50 gives you 100. And what's now the area that this encloses? You would do 38 times 12, and then you get 450 feet, right? Or square feet. Is that making sense? So by choosing like both of these rectangles have the same in both of these rectangles, you're using the same amount of fencing material, right? Because the perimeter in each of them is 100 feet, right? But they're giving you quite different areas, right? And so if you since you're already spending the money building the fence, you might as well try to enclose as much area as possible, right? Because like that way you can put the most number of plants and things like that. Is that making sense? Um, So the question is like, how do you know? I mean, I gave you two examples, but there are other configurations. Like you can play with 100 feet to break it into different pieces. How do you know that? I mean, maybe there's another choice of size that gives you even more area than 456. So in fact, there's like a solution. I don't know how obvious it should be, but what do you think would be if you had to give it a shot? What should be the best option to do? It has to be a square, actually. Yeah, so it should be a square. So what I'm claiming is that if you choose a square, what happens in the case of a square? Um, each side would be 25, 25, 25, 25, right? And if you do that, 25 squared would give you 625, I think. So my claim is that if you did this as a square, then you would if you build the garden as a square, then that's the garden that encloses the most area. And you see, that's like a very first, like the first thing that you should ask is like, how can I be absolutely sure that it should be a square, right? I mean, I'm just claiming it, but like we would like to have like a way to make sure that that's the case. So that's the first thing to do, and oh yeah, I guess that's the only thing that I want to check here in this particular example. But you see, like it gives you like a very like we'll see that with calculus the problem it becomes very easy to solve. Uh, in fact, this one doesn't even require calculus. You can do it without calculus, but there are other problems where maybe I don't want the shape of the garden to be a rectangle. Maybe you want it to be like a pentagon or something else. And then like without calculus, the problem would become super complicated, but with calculus, it's like super easy. Okay. So how can you set up this problem? Well, the way to set up this problem is to say, well, I don't actually know what the sides should be. That's what I'm trying to determine. So let's just call the sides X and Y, right? And so what's the area? The area is going to be X times Y, right? But this X and Y, right? There's like a relation between these two variables, right? They're not completely independent. What's something that we know? How are X and Y related? There's something that we do know about them, right? What can we say about X and Y? But how much they relate to one another? Well, let me put it this way. What should x plus y plus x plus y should be? Uh, yes, but that should be equal to a single number. Like in each of these examples, what was the sum of the sides equal to? It should be equal to 100 because we're trying to build the fence, right? This is the total fence, so they should add up to 100 because I'm like the conditions of the problem are that you want to spend 100 as make a fence worth 100 feet, right? Long. Is that making sense? It is true. It's also that it's 2x plus 2y. That's convenient. Or another way to say that is that x plus y should be 50, right? Or another way to say this is that it's 50 and y is 50 minus x. So what I'm trying to say is that once you know one side, the other is completely determined by the fact that you want the perimeter to be 100. So is that making sense? That's kind of like the important thing to realize in this problem. Is that okay with everyone? And so that what does that mean? That means that the area, which was in terms of x and y, is actually, you can think about it just in terms of x, right? So the area is really just a function of x, which is 50x minus x squared. Is that making sense? So we're trying to find the value of x that gives you a max for A. Because once you have the max for A, that's the maximum area that you can enclose. So we're trying to find where A of x achieves a maximum. Is that okay? Is that making sense? So how do you find the max of a function? What do you have to do? Well, you need to find the critical points. The max and the mean can only occur at the critical points. So we should find the critical points for this function. So it only has, so there's only one critical point. Or x equals 25. But if x equals 25, y remember was 50 minus x, so y becomes 25, right? So that means that both x and y are the same, so that's why you get a square, right? Is that making sense? I mean, in fact, that was a critical point. We have to check, strictly speaking, we have to check that it is a max. So how can you check that it is a max? You can use the second derivative. What is the second derivative of A? Well, you just take the derivative of this again. So this is -2. So that means that the function is concave down. Right, so that actually means that the critical point has to be a max. Is that making sense? Let's see. Let me do another one here. Give me a second. I'm trying to find a fun problem for you. Oh yeah, this one is nice. This one is a cute problem. Okay, yeah, I like this one. Let's try it. So yeah, let's do this one. So when you so there's like this physics problems about projectile motion. So here's another example. About projectile motion. Okay, so here imagine you have like a cannon or a ball that you can throw. So here you have like a cannon, or you're just throwing a ball. So when you throw a ball, you can throw it at different angles. So maybe, for example, here I'm going to throw it. Let's say this could be like 30-degree angle. Maybe it lands here. Maybe when you throw it at a different angle, very steep, it lands here. When you throw it at a different angle, it lands here. Okay, so what I'm trying to say is that when you throw a ball, right, depending on which angle you throw it at, the ball will land differently. And hopefully, I mean, I'm sure like everyone has had that experience. where like, the ball will just end up being in a different location, depending on how you land it, throw it. So that's called the range, like how far away from where it lands from where you throw it. So the range. So let me just draw like a more clean clean picture. So if you throw it at an angle of theta with respect to the floor, the range is like is this thing called R. This is called the range, and that's just like the horizontal distance traveled by the ball. Is that making sense? Is it clear what the range is? So there's like a formula for the range. So as I was saying, the range depends on the angle, and the formula for the range is that it is, let me write it here. Okay, so here in this formula, theta is the angle, and in this formula, g is what people like the physicists call the acceleration due to gravity. I don't know if anyone knows what this value is. Anyone knows what the value for g is? In case someone has seen this before. It's 9.8 like meters per second squared, yeah. But it's just like a constant, like, right, it's 9.8 meters per second squared, but it isn't better. It's nicer, more elegant to leave it as a constant, even if it's, I mean, as a letter, instead of like replacing it with 9.8, that's what I'm trying to say. So it's just a constant. And v is kind of similar. V would be the velocity at which you're throwing the ball, which we are assuming that you're throwing all of these at a constant velocity. So v is just like the velocity of the ball, which is constant, which is also constant. But it's just more elegant to leave it in terms of v instead of replacing v with 10 feet per second or something like that, because like then you get like more nasty numbers. So it's also constant. So like this only depends on theta. So these two are not variables. They're just like, they're constants. It's just that I'm choosing not to give right explicitly the numbers for these constants, because then like the formula kind of looks less elegant than as of now. So like a classical optimization problem would just be to determine the angle theta that gives you the maximum range. So again, this is a problem about finding a max. So the way to find the max is essentially the same way as I found the max in the previous example, by setting the first derivative equal to 0. So I'll give you like 3 minutes to think about it on your own, and then I'll tell you what the solution is. Let's take 3 minutes for you to work it out. So was anyone able to find the angle? What should the angle, which you throw it should be? What is the derivative of this function? Again, these two quantities are constants. They have no derivatives. You just give it the constants. What's the derivative of a sine? The derivative of sine is cosine, right? So you get cosine of 2 theta times. Is that all, or am I missing something? Is that the full derivative, or is there something else missing? Times 2 because of the chain rule. So it should be times 2. Is that making sense? When is this 0? So you need v squared over 2 over v squared g times 2 cosine of 2 theta equals 0. Again, these are just positive numbers, so they're never 0. None of these are ever 0. So you actually need the cosine of 2 theta to be 0. So for what angle is the cosine 0? At what angle is the cosine 0? You actually need 2 theta to be 90 degrees or pi over 2 because cosine of 90 degrees is 0. Is that making sense? So what this is saying is that if you want to throw like a ball, if you're throwing balls, all the balls you're throwing them are with the same speed. You're always throwing them at 10 feet per second or whatever. You're throwing a bunch of balls at 10 feet per second. The way to throw it so that it covers the most horizontal distance is by throwing it at a 45-degree angle with respect to the floor. Is that okay? Is that making sense? So how can you check that this is a max? To check this is a max, you can use a second derivative test. So for that, you find the second derivative. So you have to take the derivative of this function. Again, it's just taking the derivative of a cosine. The derivative of a cosine is minus sine. So you get v squared over g times minus sine of 2 theta times 2 because of the chain rule. So this gives you minus 4 v squared over g sine of 2 theta. So if you take if you evaluate the derivative of the critical point, what is the sine of pi over 2? Anyone remembers this? What is sine of 90 degrees or sine of pi over 2? It's just 1, so you get minus v squared over g. This is a positive quantity, so this number is negative altogether. So that means that the second derivative is negative, so you're sad. And if you're sad, you get a max. So it does yield a max by the second derivative test. Is that making sense? So all this, I probably should do 1 or 2 more optimization problems tomorrow just to make sure this is okay. But all the optimization problems kind of have like a similar flavor where you know, you have you find like a function, or you're given a function and you want to find them. I'll try to do tomorrow where it's maybe more natural to find the mean of a function. So you have a function, you want to find the max or the mean of that function. And for that, you find the critical points and then use the second derivative test to check that that critical point is either a max or a min. Okay, but yeah, we should continue doing some more examples tomorrow about this. But it's one of like the classical problems of calculus to find to solve like an optimization problem. So tomorrow we'll continue, as I said. So tomorrow we'll continue with this, and depending on how much time we'll have left, I'll tell you some other stuff. But I think it's a good place to end. Set the announcement in a couple of minutes.